Welcome back to our next unboxing. We have a special treat today, so let's just get right into it. I've heard a lot of good things about this. Let's see what we have. It's a final exam. Math 265, that's our multivariable calculus final. Let's see what we can see. It's fall 2019. Now that was a great semester. A lot of good things happening in fall 2019. It was sort of a transition semester. Before that semester, they had slightly different policies about dropping problems. They didn't drop any problems. And after that semester, they changed the policy, made it even stronger in some sense. So this was a nice vintage. The paper, it's actually a gray. You can kind of tell the distinction here between white versus gray. You might think, what's great about gray? Well, really great for low visibility light. If you're in a dark classroom when you're taking a test, has really good coverage, does not bleed very well. It's one of my favorite colors to work with when taking a final exam. Now, if we take a look here, we can see, check it out, double-sided, a really nice feature. See, that's environmentally conscious. By using both sides of the paper, we've cut down the amount of paper needed. It also makes it a little bit lighter. So when you're walking up to the front of the class, it just doesn't weigh you down. And so we want to get into this test. Of course, if we want to explore it, we need to open it up. So let's start. We're going to open this test up here, and we're going to go through it and take a look at these problems. And I think these are going to be some fun problems here. Of course, there's always a good time whenever you're doing a calculus class. All right, so let's go through and let's see what we have. So we'll start with our first problem. I guess it's a classical way to go about solving problems in order. So, number one, consider the function x squared minus xy plus a half y squared plus 3. And part A, find the tangent plane to f of xy at the point 3, 2, f of 3, 2. Now, there's really a couple ways to find the tangent plane. Now, this is a nice format here where we have z equals f of xy. And the best way to find the tangent plane is to say that z is the function of the point, AB, plus f sub x at AB times x minus a, plus f sub y at AB times y minus b. So what do we need to do? Well, what are our a and b? In this case, our AB is 3, 2. So that's the point. So we're going to go ahead. We're going to start by writing down our function. And it's already written down, but we want to write down again just as a reference here. So x squared minus xy plus a half y squared plus 3. Then now we have our f sub x. Take here with respect to x. We're going to get 2x minus y. And, well, that's it. F sub y. Well, no y there. We'll get a minus x, and then we'll get a plus y. And now, what happens next is we need to evaluate to get these three values here. So, plug in 3, 2. So, we plug in x equals 3, so that's 9. 3 times 2, 6. A half times 2 squared, 2. 3, turns out still 3, and that becomes 8. And then f sub x at 3, 2. Well, 2 times 3, 6. Minus 2 makes 4. F sub y at 3, 2. Minus 3 plus 2, which makes negative 1. Now we can put those values in. So we get that our tangent plane is 8 plus 4 times x minus 3. And then minus 1, so just write that as minus. And y minus 2, because that's y minus b. And that's part A. Okay, good. Nice. Now part B says, use the tangent plane from part A to approximate the value of the function f at the point 2.75, 2.2. Well, that's 11/4, 11/5. So how do we do that? Well, the answer is this tangent plane here is an approximation. So really, whenever you see the word approximate, you always think about what's the tangent. In one single variable calculus, it's tangent line. Multivariable, it's tangent plane. So our idea is that f of xy is approximately 8 plus 4 times x minus 3 minus y minus 2. So then we can say that f of 2.75, comma 2.2, well, that's approximately 8 plus 4, 2.75 minus 3, minus 2.2 minus 2. So that's 8. If I take 2.75, subtract 3, that's negative 0.25. So 4 times negative 0.25, and 2.2 minus 2 is 0.2, so minus 0.2. So this is really minus 1. So what do we have? We have 7, because that's 8 minus 1, subtract 0.2, and so that would be 6.8. And that would be the answer to number 1. All right, well, that's not so bad. A nice warm-up. Let's go to number 2. So a solid is formed by the set of points with z greater than or equal to 0, so we're above the xy plane, and x squared plus y squared plus z squared is less than or equal to this capital R squared, the upper half of a solid sphere of radius r. So we can give a quick sketch of that. So we have half a sphere. Radius is r. So we have this solid. All right, so there's our shape. Now, what are we going to do? The density is given by 3z cubed, and the mass is 16 pi. The question is, what's r? So normally, we kind of do it the opposite way, is that we have our region, and we're going to start with the density, we find the mass. But now they've told us the mass, and we're going to try to figure out, well, what exactly is our region? And so the idea here is, well, we have the mass. We just have to figure out what the right parameters are. Now, one of the things we should figure out is what we're doing. So 16 pi, that's our mass. That's what we're told. And if you want to find mass, you integrate over your solid of your density function, dv. Now, the question is, well, how do we actually integrate this function? So this is the integral over our solid of 3z cubed dv. Well, we have to make a choice. What coordinate system should we be using? And here, well, we have a sphere, a top half of a sphere, so let's go spherical. So we're going to work in the spherical coordinate systems because spherical coordinates are great for spheres. In fact, for spheres, it's really easy to describe. We go all the way around the z-axis, which means that we go 0 up to 2 pi. We're in the top half above the xy plane, which tells us that phi goes from 0 to pi halves. So remember, phi equals 0 straight up, and then we come off the z-axis, and by the time we hit the xy plane, that's at pi halves. So 0 to pi halves. And what about rho? So rho goes out to the edge of the sphere, and we are a sphere of radius r. So 0 less than or equal to rho, less than or equal to capital R. So that's going to be our setup. We have our dv. Well, that's not so bad. We just have to think of the song. We have rho sine of phi, d rho, d phi, d theta. Life is good. What about z? Well, z is rho cosine phi. Okay, so we're going to use all of that to rewrite what we have. So what do we have? We're going to do integral, integral, integral. We get 3. Replace z by rho cosine phi cubed. Our dv, rho squared sine phi d rho d phi d theta. So the outer one is our theta. That goes 0 to 2 pi. Our middle is our phi, 0 to pi over 2. And our inner is rho, 0 to capital R. We don't know what capital R is. So what do? Well, we do what we almost always do, which is we group things together. The 3, not so clear what that's going to be attached to, so we'll just put it all the way out front. So we have 3. And notice our bounds. These are really nice bounds. These are the kinds of bounds that we want to take home to meet our family. So what do I mean? Well, they're just numbers, which means we can pull our integral apart because the functions are easy. So if the theta, well, there's really no theta here. So that's integral 0 to 2 pi d theta. How about phi? Well, 0 to pi over 2, you get a cosine cubed phi, and then a sine phi, d phi. All right, how about rho? Well, 0 to r, you get rho cubed and another rho squared, makes rho to the 5th, d rho. All right, so now we've got to go through and work through each piece. Now, some of these are pretty easy. That one is easy, 2 pi. Don't even have to think about that one. Here, what would we do? Well, if you let u equal cosine, then du is negative sine. Or if you like, minus du is sine phi, d phi. All right, so what does that mean? That means this becomes the integral of cosine 0, 1, to cosine pi half 0 of minus u cubed du. Well, that's not so bad. That's minus 1/4 u to the 4th, evaluated from 1 to 0, which is 0, because if you plug in 0, you get 0, minus 1/4. So that says that this middle integral, lo and behold, is 1/4. Now this last integral. Well, that's not bad. That's 1/6 rho to the 6 from 0 up to r, which gives us 1/6 capital R to the 6. All right, so we have, putting this all together, so this tells us we have 3 times 2 pi times 1/4 times 1/6 r to the 6. Well, we can take the 3 and the 2 and cancel with the 6. So we get pi over 4 r to the 6. And remember what we said. That's equal to 16 pi. So that's equal to 16 pi. So move things around. So the pi's can cancel. Multiply the 4 across. R to the 6 has to equal 64. Well, so what is R? So R would be 64 to the 1/6, which means I'm trying to come up with some number such that when I raise it to the 6th power, I end up with 64, and there is such a number. It's called 2. And that's the answer. Now you might notice, wait a second, this is our second problem, and the answer was 2. Classic Easter egg. Classic Easter egg. They oftentimes like to slip these in on exams where they say, oh, maybe we'll make the answer the number associated with the problem. It doesn't happen all the time. But, you know, just once or twice they like to throw it in and see if people are paying attention. All right, so that was number 2. Let's turn over. Let's see what number 3 says. Evaluate the integral along the curve f dot dr, where f is, it's a vector valued function, 2x over y, and 1 minus x squared over y squared. And c is the path 1 plus cosine pi t over 2, comma 2 minus cosine pi t over 2, where 0 less than or equal to t less than or equal to 1. This is actually not such a bad integral to do directly. The cosine pi t would make it unpleasant, but we could probably suffer through it. But let's not suffer through it. We should always check. Whenever you see an integral along a curve, the one thing you hope for is it conservative? All right, so how could we check? Well, one thing is you could take partial derivatives. For instance, take the derivative with respect to y of this first term, compare it with the derivative with respect to x of the second term. But the other way is to think, okay, suppose this were conservative. Well, what would have to be true? Well, that says come to the first slot, that would have to be the derivative with respect to x. If you were to integrate this with respect to x, what would you get? The answer is you'd get x squared over y. All right, well, that's not too surprising. Now go to your second slot. Well, this would be the derivative with respect to y. And suppose you were to integrate that. Well, the 1 minus x squared, I can treat that like a constant. And I say, okay, what's the integral of 1 over y squared, or rather antiderivative of 1 over y squared? And the answer is it would be minus 1 over y. And if you rewrite that, that's the same as x squared minus 1 over y. Now, can it be conservative? Well, you compare the pieces. So the part here, x squared over y, you'll see that's also in the second piece. So that's consistent. The other thing, the 1 over y, well, that's just in the part with y, which is perfectly fine. So it is conservative, and in particular, we see that capital F is the gradient of x squared minus 1 over y. So we are dealing with a conservative line integral. That's the best kind of line integral. Now we need to figure a couple things out. Where do you start? Well, that's t equals 0. So we plug in t equals 0, we're going to get cosine of 0, and cosine of 0 is 1. So we start at 2 comma 1. Where do you end? Well, that's t equals 1. Cosine pi halves is 0, so we're going to get 1, 2. So we have that the integral along the curve of f, integral along the curve f dot dr is equal to, we take our potential function, x squared minus 1 over y, and we go from our start point, 2, 1, to our end point, 1, 2. So, when you plug in 1, 2, you're going to get 1 minus 1 over 2, and then we're going to subtract 4 minus 1 over 1. Well, first term goes away, 4 minus 1 is 3, and then it's a minus that, so minus 3, and that's the answer. And look, oh my gosh, 2 problems in a row. You get a 3 on problem number 3. I doubt that's going to continue, but enjoy it while you can, right? Okay, next one. Problem number 4. Use the method of Lagrange multipliers to find the maximum and minimum values of this function y minus x, given that x squared plus 2xy plus 3y squared equals 3. Now, one of the things you always wonder when you're looking at a problem is what technique should we use? I think on this problem, the technique we should use is Lagrange multipliers. You're probably wondering, how did you know that? And the answer is it tells us. So you should oftentimes pay attention. And if the problem says, use such and such a technique, you should probably use that technique. So how does Lagrange multipliers work? Well, we're going to think of this as our constraint function, g of xy, and we need to have f sub x equals lambda g sub x, and f sub y equals lambda g sub y. So f sub x is negative 1. That's going to equal lambda. G sub x is 2x plus 2y. F sub y is positive 1. That's going to equal lambda g sub y, which is 2x plus 6y. So, when in doubt, solve for lambda. So we get that negative 1 over 2x plus 2y has to equal 1 over 2x plus 6y. So notice I just divided across. Now from here, clear your denominators. So minus 2x minus 6y equals 2x plus 2y. And we move some things around. And if we do that, we're going to get that minus 6y minus 2y is minus 8y equals 2x plus 2x equals 4x. Or we can say that x has to equal negative 2y. All right, now this gives us a new relationship. Now what do we do with it? Well, we plug it back in to that relationship. So I'm going to replace every x by minus 2y. So minus 2y squared plus 2 times minus 2y times y plus 3y squared has to equal 3. So the first term becomes 4y squared. The second term becomes minus 4y squared. The last term is 3y squared. These terms cancel. We can divide it by 3 and conclude y squared equals 1. And now we know that y is the square root of 1. Really, it's either plus 1 or minus 1. So we have 2 points. One point where y equals 1, one point where y equals negative 1. How do you get the x-coordinate? Well, to get the x-coordinate, you come back to this relationship. So it says x is negative 2 times y. So negative 2 times 1 would be minus 2. Negative 2 times minus 1 would be positive 2. So these here, these are the points where the min or max could potentially happen. Now, you might say, must it happen? Well, it depends on the curve. And in particular, is this collection of points, must there be a min and max? And it turns out that there is a min or max for this collection of points because this is really just an ellipse turned sideways. And the reason why that's important is it says you have something which is closed and bounded, and that means there is a min or max. So, we're not done, because we weren't after the points, we were actually after the values. So the last thing to do is we plug these in. So we're going to plug in 2, negative 1, and negative 2, 1. So when we plug in 2, negative 1, what do we get? Well, we get the y minus x, negative 3. Negative 2, 1, we get y minus x, positive 3. And we say, all right, look on our list, which one's the smallest? Well, negative 3, that's our min. Which one's the largest? Is positive 3, that's our max. And that's our answer. Negative 3, positive 3. Life is good. Life is good. All right. Number 5. A thin sheet of metal has the shape of the surface, z equals 2x plus y squared, restricted to the portion that lies over the triangles with corners 0, 0, 2, 0, and 2, 1 in the xy plane. Let's go ahead and just sketch that triangle really quickly. 0, 0, 2, 0, 2, 1. So there's our triangle. So here's our region R. All right, now what's next? Assuming that the density is 1 plus xy plus z squared set up, but do not evaluate. The sweetest words in a calculus exam. Do not evaluate. The integral for calculating the total mass of the sheet. The answer needs to be an integral with bounds only in terms of x and y. So our final answer can't have any z's involved. There's no z's. Now let's pause for a second. Notice what we have. We have a surface. This is a two-dimensional thing. So we're really going to have a two-dimensional integral involved here. And we're only going to have it in terms of x and y. So what's happening is we're doing a surface integral. So we have to remember what does a surface integral do? Well, in particular, what surface integral are we after? If we're after mass, it's like what we just talked about a minute ago. It's a double integral over our surface, which we'll call our surface G for right now, our density, x, y, z, dsa. So what we need to do is a couple of things. Well, what is our dsa? That is the surface area piece. So that's 1 plus f sub x squared plus f sub y squared dA, where we integrate over r. So in our case, if we come here, f sub x is 2. And f sub y is 2y. So, and the 1, by the way, is 1. So this will become 5 plus 4y squared, all underneath the square root sign. So we get integral, integral, our density function. Well, our density, that's 1 plus xy plus z squared. Now, what do we do with that z? Because we have to be only x and y. The answer is we use our relationship. That relationship 2x plus y squared. So we get 1 plus xy plus 2x plus y squared squared. Okay? That's our integral. Our DSA, square root 5 plus 4y squared dA over the integral region R. Last thing to do, actually set up our bounds. So integral 1 plus xy. We don't have to expand this because we're not actually integrating it. We just have to make sure our pieces are there. And we have to pick, and there's two choices. We'll go ahead and do our traditional dy dx because that's sort of our go-to. X goes 0 to 2, so that's our outer bounds. And then if we pick an x, well, we're going from y equals 0 up to this line. What is this line? Well, if we look at it, it goes through the y-axis, so it's y equals something x. And to find it, well, we go over to up 1. So rise over run is half x. So 0 to 1/2 x. And there is our integral. And that would compute our total mass. That's it. We've set it up, and now we're done. And we can move on to the next problem. So what's our next problem? Number 6. Decompose acceleration in the form a sub tt plus a sub n for a particle traveling according to the position function r of t equals this at t equals 0 without finding t and n. So what are we finding? Well, really we want to find a sub t and a sub n at time t equals 0. Now there's two ways to do this. There's the geometric approach and there's the algebraic approach, and they're about the same. So we just flip a coin and let's see. Well, let's do geometric. Okay, so how do we do geometric? Well, we're going to start with our r of t. So that's 2t squared, comma, 2t plus 2/3 t cubed, comma, and 2t minus 2/3 t cubed. We're going to look at r prime of t. So that would be 4t, comma, then 2 plus 2t squared, 2 minus 2t squared. Our double prime of t would be 4, comma, and then 4t, comma, and minus 4t. Now, what's next? Well, the next thing is we want to take a look at r prime of 0, which is 0, comma, 2, comma, 2, and r double prime of 0, which is 4, comma, 0, comma, 0. Now, why do we want to do that? Because remember, we're looking at a specific time. And when we're looking at for a very specific time, we can evaluate our r prime and r double prime. Now, a sub t, by definition, that's r prime dot r double prime over the magnitude of r prime. So that's 0 to 2 dot 400 over the magnitude of 0 to 2. But notice this dot product. We're going to get 0, 0, 0. So a sub t is 0. Done. All right, how about a sub n? Well, a sub n says take the magnitude of r prime cross r double prime divided by the magnitude of r prime. All right, so let's do some work. So we're going to take 0 to 2 cross 400. So let's see what that would be. So that would be ijk 0 to 2 400, and well, I times 2 times 0 is 0, j times 2 times 4. That would be 8j. K times 0 times 0 is 0. 4, 2, and k, that's 8k. But subtract, so minus 8k. 0 to I, that's 0. 0, 0j is 0. All right. So we end up with 0, comma, 8, comma, negative 8. All right, so now what? Well, what's the magnitude of 0, 8, and, negative 8? Well, that's the square root of 0 plus 64 plus 64. Now, really, you can pull out the 64, and all the way out becomes 8 and the square root of 2. Now, downstairs, magnitude of r prime, 0, 2, 2. Well, that's the square root of 0 plus 4 plus 4. Again, you can pull the 4 out. Square root of 4 is 2, and there's a square root of 2 left. So, this becomes 8 times square root of 2 divided by 2, square root of 2, which leaves us with 4. So there's our answer. A sub t equals 0, and a sub n equals 4. All right, good. Now, really, this advantage of geometric is when you're evaluating at a particular point. If we were trying to find it for all time, we probably would not want to do it geometric. Algebraic would be a little bit faster. But we use what we want, as long as it's correct. There's more than one way to do a problem. Number 7, let S be the boundary of the cylindrical region D given by x squared plus y squared less than or equal to 4 and 0 less than or equal to z less than or equal to 3. So what we have is we have a cylinder that has some shape, something more or less like this. So here we have z equals 0 up to z equals 3. We have our z-axis running through here, and all right, so there's our shape. Now, and we should point out our radius here is 2, because 4 is 2 squared. If you have this vector valued function, x cubed z plus 2y squared z in the I, x squared z plus y cubed z in j, and x squared plus y squared k, find the outward flux across S. Well, what is that? We're trying to find flux through the boundary of a solid. So this is saying, do we know how to use divergence theorem? So we're not going to compute flux through the boundary of the solid by actually doing a surface integral. We're going to do divergence theorem, and says that this is equal to the integral over the solid D of what? The divergence of F dV. And when we say this, we can actually write down what we were originally going to do. So originally the problem says find the flux, which means integrate on the surface of our F dot n dSA, or d sigma if you're short on space. All right, well, that's good. So what is the divergence of F? Hopefully, it's something pretty nice. Well, go through, come to the first term, derivative with respect to x. That term's completely gone. You get 3x squared z. Go to the second term, take derivative with respect to y. That term's completely gone, and you get 3y squared z. Go to the last term, take derivative with respect to y. Well, there is no y. And so that's it, dv. Now, of course, you can factor out a 3z, and you get x squared plus y squared. Now, well, we don't really have any symmetry. We actually have to do this integral. And how would we do this integral? Well, this one is a very strong candidate for doing it by cylindrical coordinates. What's the clue? Well, the big clue is it's a cylinder. If you see a cylinder, cylindrical is really good. In particular, you have this nice symmetry when you spin around the z-axis. When you have that kind of symmetry, it's not in a sphere. We oftentimes say, let's do it in cylindrical. All right, so let's figure this out. Well, what do we have? Theta, that's easy. That's 0 to 2 pi. How about r? Well, that's going to go 0 out to 2, radius of the circle. How about z? Well, that's 0 up to 3. What about our dv? Well, that's r dz dr d theta. And probably z, well, that's just z. That's a nice thing. X squared plus y squared, well, that's r squared. So let's put this all together. So that says we need to do the integral, integral, integral. We're going to get 3z r squared dv r dz dr d theta. And we use our bounds. So theta, 0 to 2 pi. R goes 0 to 2. And z goes 0 up to 3. Now if you look, again, this is the kind of integral where we have these nice bounds. So we'll pull it apart. Why not? 3 integral 0 to 2 pi d theta. By the way, if you don't like to pull integrals apart, you don't have to. Do what you're comfortable with. And as long as you get the right answer, then you're fine. And if you don't get the right answer, do a different thing. So, all right. So we have r cubed because we have r squared times r. And then the other thing we have is we're going to have integral of 0 to 3 of z dz. So the first integral, that's easy, 2 pi. Second integral, well, that's 1/4 r to the 4th from 0 to 2. And if you plug in 2, 2 to the 4th is 16 times the 4th, leaves us with 4. Here we're going to get a half z squared from 0 to 3, which, plug in 3, you get 1/2 times 9. And if you plug in 0, you get 0. All right, so we're ending up with 3 times 2 pi times 4 times a half times 9. The 2 and the half cancel. 3 times 9 is 27. So we get 27 times 4 times pi, and 27 times 4 is 108. So that tells us that our flux is 108 pi. And that's our answer. Okay, which brings us to number 8. Number 8. Let S be the upper hemisphere of x squared plus y squared plus z minus 3 squared equals 9. So that's the part where z is above 3. So let's sketch that. So we have a whole sphere. If we took this equation, x squared plus y squared plus z minus 3 squared, it's centered up here at 3. But we don't want the whole sphere. We want the top half. So there's our equator, and then we just want the top half. All right, so we have our surface here. All right, and upward pointing normals. So that says our normals are pointing up. Okay, cool. Now we want to calculate the integral on the surface del cross f dot n d sigma. D sigma is just another notation for dsa, where f is this particular vector valued function. Now notice that this surface, this is a nice surface in that it's a surface with an edge. In other words, this is a surface with a boundary. Now, when you have a surface with a boundary, you have Stokes Theorem. And Stokes Theorem says you can do the integral that you were originally given. And by the way, you almost never want to do that. If they're giving you the problem, the reason they're giving it to you is because this is the hard way to do it. One option is you can say, well, let's look at the integral on the boundary of our surface of f dot t ds. So that's what Stokes' theorem says. And so in other words, you come to this and you ask, okay, how do you orient the boundary? Well, it turns out you would orient it counterclockwise as viewed from above. And the reason you orient it in that way is you'd have to base it on what's happening in regards to the orientation on the surface. All right, now, that's one option. I almost always prefer to do the following, which says, let's not do that. Instead, let's just choose a better surface. So what's a better surface? Well, I have the edge of my surface. It's just a circle. So you're up here in three-dimensional space. So I can say, well, what's the better surface that fits that piece? And the answer is just put in a flat disk. Now, if I put in a flat disk, what's the way that the normals point? And the answer is they'll point up. And the one way you can visualize this is just think about deflating this balloon. So as you deflate, what happens is that the normals will follow along. So if that the normals were pointing up, when you deflate it down to something flat, they're still going to be pointing up. So let's do that. Now, what's nice about this? Well, it's very flat, so the normal is just simply 0, 0, 1. And notice it has length 1, because that's a unit normal. So, all right, so we're going to we're going to do the following. Let's call this surface G. So we're going to find the integral on G of del cross F dot 0, 0, 1. All right. Well, let's find del cross F. And really, we could just find del cross F with just that last entry, but we'll go ahead, we'll find all the entries. Why not? We've got the time. Well, I think we have plenty of time to finish this exam. So del cross F, so that's going to be, we have our I, J, K, partial x, partial y, partial z, minus yz, xz, z cubed, minus x squared y. So I, partial y, minus x squared y. So there's a y shows up there, so when I take the derivative with respect to y, I'll get negative x squared in the I direction, j, partial z, of minus y times z. So that would be minus y, and that's in the j direction. K, partial x of xz, well, that's going to be z, and that's in the k direction. And now, other ways, so going up, partial y of minus yz is minus z. But because of the direction, we subtract minus z, which really makes it a plus z. Partial z of xz, well, that'll be x, that's I, but we have to subtract, so minus xi. And the last thing is partial x of z cubed minus x squared y. Well, there is an x here, so that would be minus 2xy, but because we're in that direction, we really add 2xy, so plus 2xy j. So we end up with minus x squared minus x, comma, minus y plus 2xy, comma, 2z. So there's our del cross F. So if we dot that with 0, 0, 1, 0, 0, 1 times that means that really we need to find the integral on G of 2z. Well, that's not so bad. In fact, it gets better. Let's look at z. Notice z is flat. It's always the same height, and the height is still 3. So z is always 3, which means that this is 6. It's a constant, and I can pull out. So that's 6 times the integral g d sigma. Well, that's 6 times the area of G. Well, what is G? It's a disk, and it's a circle. It's a circle of radius 3. So the area of a circle of radius 3 would be pi times r squared, 3 squared. So 6 times pi times 9 leaves us with 54 pi. And that's the answer. And we're done. We're done with that problem, but in fact, that was our last problem. So we are done now with our entire exam. It was a good exam. A lot of fun. A lot of fun. So we should write down, we'll put a name down. So we'll put down Yo Iduk, which is Hungarian for good times. Good times. Because it's always a lot of fun whenever you're doing a calculus exam. So that's it for this one. And I'd say a fun test, not so bad. A little challenging here and there, but overall, good times to finish our semester with. And we'll see you next time when we unbox our next exam. All right, take care. Bye.